Next up, we have Randy Chase from Tomorrow IO talking about ICGen.
Thanks, Kyle. Yeah, today I'll be talking, continuing the theme of private sector AIDA methods and a project that we've called ICGen internally as like initial condition generator. So for those who don't know what we're doing at Tomorrow, one of the big parts of our company is this microwave sounder suite. And if you're interested in the actual size of the instrument, we have one hanging over our booth. It's about the size of 2 cereal boxes kind of stacked on top of each other. And we've recently reached our goal of hourly updates globally. And we have 11 of these little toasters on orbit that are collecting microwave information. And if you're unaware of the microwave spectrum and what it gives us in numerical weather prediction, is that at the microwave wavelengths, you're less sensitive to cloud scattering. So essentially, you can then retrieve things like humidity and temperature profiles, even when there are some clouds obstructing the view of the satellite, which then you can imagine you can then retrieve more information for your NWP and push it towards the observations over a wide swath of the globe. Specifically, if you're interested in instrument characteristics, I would encourage you to see Joe Munchak's talk tomorrow on the instrument and the constellation status, as well as I'm sure he's going to talk about some future plans as we go forward. But just a quick overview here of the rough spatial resolution of the satellites. For the highest frequencies, we're getting at about 15 kilometers, and then the lowest frequencies at 89 gigahertz are 30 kilometers. And for an example, if you're wondering why are we in the space of launching a constellation of microwave satellites, the animation here provided by Joe is the government fleet of microwave sensors. I believe this is 89 gigahertz, and you'll see that there are lots of gaps that occur from this government suite of sensors. What happens when you end up adding in 11 of these similar satellites? You tend to start to close in on a lot of these gaps. So the basic premise here is that if you have rapidly updating observations in the microwave spectrum, you can then again fit your curve of your trajectory to then push the model into a better forecasting space. But one key thing that I think the community has not been ready for is the sheer volume of the new data. I think we've always had the issue of computational demand in our field, especially DA. There's a reason why the IFS and GFS don't run every hour like the HER. You simply cannot mesh in all the observations you can. And I think the statistic that everyone throws around is something like 90% of observations aren't even included in DA anyway. So I beg the question here of how can weather forecasting best leverage this new volume of data? And luckily, the previous talk kind of set this up nicely. It's this idea that you need a fast method that can update rapidly. And the methods that lend themselves to do this is AI and ML. So 5 years ago, this volume of data, this would be something that I'm sure NWP practitioners would just balk at, and you wouldn't want to even try it because it's like the computational demand wouldn't be there. And then sure enough, our AI ML revolution has kind of occurred to enable such a thing. So the general idea here of ICGen is to take some past weather state, so your background, your 6-hour-old analysis, or maybe a 6-hour-old forecast. We also want to leverage the pre-existing work that the NWP is working on. We don't want to reinvent the wheel, especially as a team of about 5 to 6 people at Tomorrow. We're not going to reinvent and take all the obs and do it ourselves. So we take the pre-existing analysis or old forecasts, and then we kind of like massage in our TMS data. We use some data-driven method, get the current state, and then use some other pre-trained weather model, Aurora, ForecastNet, Windborne, whatever pre-trained model you would like to use. So you might be asking, what's the method you're trying to use? And we sought out originally this score-based data assimilation paper that was written by Rosette and Lupe in 2023. And if you're unfamiliar with score-based diffusion, essentially what falls out of the diffusion model itself is you can use Bayes' rule. So you train the diffusion model to say, hey, can you generate some random weather state? So it looks at millions and millions of examples of weather states from ERA 5, and then it generates some random weather state from those. And then at inference time, you can actually use Bayes' rule to guide that weather state towards your observation. So you kind of get a free guidance from the diffusion model without training it specifically with the observations. And here was our first toy model, which was a single level and at 1 degree. And these are specific humidity plots. And you'll see that the top is the random humidity field from 850 millibars. The bottom is then guided from TMS, which we have the swath there on the right. And you'll see that the difference between them, that red blue, is actually physically changing the state towards the observations. So this was the toy model to say, hey, okay, this method could potentially work. But again, it was coarse, 1 degree, and only one variable. And then when you try to run a lot of these traditional, like the AI weather prediction models, you actually need 70 variables or so. So scaling actually became a quick issue that we ran into. And I just want to be transparent, and I know this is quite a null result that you'll see eventually. But when you get to this scaling in a company of our size, we have a hard time scaling to this. So I think score-based data simulation could be a way of the future, but unfortunately, you'll see later that we ran into some challenges here. So we had to move into the latent space. Much like stable diffusion for AI literature, we had to compress our data from quarter degree, 70 variables, into something much smaller so we can get it to train in a reasonable amount of time. And we found this pre-trained VAE online called Cray5, and the reference is there, which then compresses it into a latent space of 256 channels. But you'll see that the spatial dimension there is 72 by 144, so an order of 10 factors smaller in both X and Y. So that's what we explored. We explored this score-based data simulation in the latent space. There's some specifics here. We used a billion parameter model with the UNet with some cross attention. We're following Keras with some adjustments from the sea bottle paper, trained it quite a bit. And here's just the score-based diffusion guidance. That original score function here falls out from the diffusion model itself. And then you can then guide the diffusion with this guiding score afterwards. So plugging it all together, initially things looked pretty good. You can see here, this is the 2-meter temperature, the 1,000 millibar humidity. And then when you take those fields and you plug it into Aurora, things seem to evolve physically, and things don't blow up and break. So everything checks the initial boxes. But unfortunately, when you dig in a little bit deeper and calculate some skill metrics, this version of ICGen was actually 50% worse than just using the old forecast. So there was kind of the old issue of, it's a 6-hour, the forecast takes 6 hours, doesn't work. It's kind of not useless, right? Sorry, it is useless. And we attributed this to two main things. That VAE I was talking about that had the nice high compression factor, then the things looked to your eye. The top left there is that reconstructed temperature field. But if you don't look at the difference between the original temperature field and the reconstructed temperature field, you wouldn't see these little patch artifacts, which are setting up our forecast for failure from the beginning. So as an alternate, we decided to move into a much more operational idea and less sophisticated as the readiness level of score-based data simulation kind of continues to grow. And instead of using the diffusion route, we were just thinking, can we just kind of more force the data in with traditional machine learning? So could you just include the TMS channels as the TMS data as additional input to the machine learning model? So you have some like 70 channels as the first block of data that flow into the UNet, and then the next 16 are our specific microwave channels that flow in there. And then the other idea that we've had is that instead of training, say, taking Aurora and training it to run on this new input that we create, I'd rather push the input towards what Aurora was created on. So we're pushing, say, the GFS state plus TMS towards ERA 5. And the idea is that since GFS is kind of far from ERA 5 and you plug it into Aurora, if you push GFS closer to ERA 5, you would then improve the skill metrics because that's what it was trained on. And ERA 5 has a much longer DA window, which should be closer to the observations itself. So the conclusion, well, some initial results that we've been digging into here. And what I'm showing here, the x-axis is all the different channels that are flowing. The y-axis is the change from the original GFS state. And we're all comparing to the ERA 5 as the truth here. And I've tried to highlight in larger size here all the different channels. So you got temperature, UV, specific humidity, and geopotential height. And you'll see when you go towards negative values is that you have less error in the ICGen generated analysis. And you'll see the different colored lines are just through training. So you'll see that the training of a simple UNet here is pushing it further, closer and closer to the true ERA analysis. And specifically, you'll see some interesting things that I didn't know occurred before, that the representation of the stratosphere in the GFS is actually very different than the representation of the stratosphere in ERA and IFS. If you look at specific humidity here, there are large shifts that are being occurred from the machine learning itself. And then just for some scale here, these are 100% differences in specific humidity Granted, they're very small up there, but they are being shifted much closer to the original era state. And I'm sure you're all asking the question of what is the impact of the TMS itself. So the way I'm evaluating this currently is I trained the network to have TMS in it. And with that TMS data, there is a mask that has zeros and ones. So that tells it where there's good TMS data, where there isn't good TMS data. And essentially you can play the game after training. You can then just zero out the mask everywhere to learn what the machine learning learned of the impact of the TMS data. Like if I didn't have TMS data, I then have to lean on something else. But so here's the same plots, but keep in mind the y-axis is now scaled very different. But you'll see that the TMS data has a clear impact on humidity, specifically the middle to upper troposphere here. And one detail that I did leave out is that currently we're only doing 5-channel mode on the satellites, and we're specifically digging into the channels that are specifically sensitive to humidity. So this is a clear signal that I was expecting, but I was making sure that it was actually there. But you can see large improvements in specific humidity and some additional improvements unsuspectingly in the lower temperature profile, which I think is kind of interesting, that your correlations between fields. And to get to the age-old question of, so you improve the analysis state, how does it actually affect the forecast? And I think that maybe we take this for granted as a meteorologist, as you always say, assume we improve the analysis state, will it always improve the forecast? And luckily this does propagate into the forecast, even in the AI weather prediction models. And something that we saw with the score-based data assimilation, you saw those token artifacts, and Aurora does a lot of fixing of the data underneath. It doesn't tell you when there's something unphysical. It'll tend to just smooth it out and fix it over multiple autoregressive steps. So what I'm showing here is the weighted root mean squared error. So your latitude weighted root mean squared error. The top plot is the 2-meter temperature. The bottom plot is 700 millibar specific humidity. The black line is just if I took GFS, ran it through Aurora, and then the blue line is with the TMS data. The red dashed line is when I mask it out to zeros everywhere. And you'll see that there is a discernible impact of the TMS sensor on the forecast. So I'll end here and just say that this is a new and exciting direction that we've taken. We've been on orbit for about a year, and we're starting to collect lots and lots of this microwave sounder data. Personally, I think the SDA approach is the more elegant route as we go towards the future in the community. And I think it just needs a bit more training and more GPUs if somebody has GPUs to share. And then we're just trying to get something a bit more operational to start. So we went with the more simple approach, much like others in the field. And here's just a fun animation of what 11 satellites can look like on orbit with our microwave data. So thank you, everyone.